Welcome to the Dutch Open Steel Award, the first edition, and hopefully not the last edition. We're sitting here in front of some tulips and some windmills. That's the only Dutch thing we want to share today with you. Milan, yes. Welcome here in the studio of Bouwen met Staal in Zoetermeer.
Thank you.
And yeah, I think Milan was the big inspiration to set up this award. Yeah. So Milan, what's the idea behind this award?
No, in these difficult times, we wanted to share with people some inspiration and give students motivation to work with steel structure issues which are relevant for the society and for steel sector. In addition, we would like to inspire people with presentations that are prepared for today. I have to say that we had excellent submissions. We have received submissions from 15 countries, 16 countries,
yeah,
15 universities.
Okay.
So it's a really excellent interest, and I hope next year's where we will have a little bit more established brand. We will attract even more people, more students, more universities. And for that purpose, we have prepared some templates. So even students who are not writing their thesis in English will have equal opportunities as those students who are writing in English.
Okay, yeah, very interesting.
Yeah.
Yes, I'm also looking forward to the presentations. I think first we start with the presentations. I think we have to thank the sponsors who made this possible. The sponsors are the SNS Intra, that's the Dutch steel fabricators who are active in the infrastructure. We have Zeeman as Austria, Severfield from the UK, and the ECCS, the organization for the internet, the European Organization of Steel Fabricators. Sponsors is also the books from Bouwen met Staal. And some years ago, we started to translate all these books into the English language. So I think they are very suitable for education. And we have now two books are translated. There's one book is Structural Basics, about the basics about the design of a steel structure. And the other one is about fire design. Of course, very important for steel structures to have a good fire design. The next sheet is the jury. Hij valt nu uit. The next sheet is the important jury. I think it's a very impressive jury. Maybe Milan, you can say something about it.
Yes, it is very difficult to see small letters from here, but we have an enormously competent jury from the universities. Mostly from the Europe and from China, and we have also very high profile CEOs of companies and research departments of the companies. I'm very thankful to all 15 members of jury who voted for these 6 members, 6 candidates who will present their master thesis in the following hours. It was very fun to work with the jury. It is interesting that 15 people voted independently of each other, and most of the candidates get more than three votes.
Yeah.
So that was a nice score, showing that we appreciate similar type of master thesis, and that will show today and illustrate our efforts.
Okay, thank you. The next slide. Okay, yeah, that's the agenda for today. After we have finished, we will have Nico Noorlander, and Nico Noorlander was one of the initiatives takers of this award. And he is from the industry, and he will say how important it is, these master studies for our industry, and what we can achieve with that, and that steel is still developing and very young material. Then we have the first part of the award. We will have 3 presentations. The presentations are all well prepared. Then we have 2 people from the jury will say something about trends in steel construction. First Olivier Vassar will say something about the sustainability future of the sustainability of steel. Olivier Vassar is beside the professor, is he also working for ArcelorMittal, and ArcelorMittal has a very interesting program for the future to make steel a more sustainable material. After that, Andreas Taras from the UK will have a presentation.
From Zurich.
Zurich.
Yes,
sorry.
ETH.
Zurich.
It's a new professor in Switzerland. It's New Power, one of the youngest professors. So he is very welcome with his presentation.
Yeah, about new technology in the steel industry.
Yeah.
Next slide, Annemarie, the next slide. Okay, that's the second part of the award. Although 3 participants will give the presentations. Every time we have 10 minutes a presentation and then 5 minutes for questions. Mostly the jury will put the questions, but I think that the people, if they want to put a question, put it in the chat. I think that's the best way to get questions into the program. Then we will have to finalize, and Milan will tell you about the voting procedure. And after that, we come to the end, and we'll give the prize to the best presentation or best master study.
Hopefully, some short talk with them.
Yeah.
Because it will be interesting to see who are the people behind these exceptionally good works.
Okay, and then we hope that we at 3:30 we are closing, and we have a very enthusiastic winner.
Yeah. But in order to be in time, we are a little bit over time already, so we have to give them.
I move,
space.
And then Nico, you can sit here. I give you the microphone.
All right.
You can say how important it is, these studies.
Put it here.
To build these very nice structures.
All right, Frank. Thanks a lot. So why is this master research work so important to the industry? Everybody who's in the construction world for long knows that it's in projects. It's often running from problem to problem and problem solving, and real time to do some in-depth research is often passed by, because then you already run into the next problem. So I think the platform of the academic world, as it was in the past and as it still is a vital, as I see it, is a vital platform in our industry to do this fundamental research and also work on innovative ideas and concepts to bring our industry forward. So I see that this award needs and must strengthen the interaction between the academic world and the construction industry. So I would like to say to all people from the industry that if we encounter problems in our construction world, that we indeed take the time and say, okay, what fundamental problem do we have here, and is this a problem that we need to put as a master thesis subject to the academic world, so that we improve the interaction between the academic world and the construction industry. So let me speak up my hope that this award will, let's say, be the how do you say that, vliegwiel, the wheel, the generator for improving this phenomena. So I like to close with that, but that's my real hope.
Yeah, thank you very much, Nico. And one of the reasons that we call this price Dutch is because, in my opinion, in Netherlands we have an enormously strong link between industry and academia, especially related to master theses, and that makes our students very attractive. Maybe too attractive because we have difficulties to keep Dutch students at universities. They go directly to industry, not only in Netherlands but also worldwide. So let's hope that this strong interaction between industry and construction sector and academia will be strengthened in the future. Maybe we have a couple of seconds to hear if we have some of our jury colleagues to add something to that, especially from the companies. Are there any reaction from the Peter or Alan or from Jan, who can underline the importance of this cooperation between academia and
construction world?
Probably not. Okay, then we go
well,
on with
okay, I could.
Yes, please.
Yes.
Yes.
Basically, I agree with everything you said. Instead of that, I'm more scared that all those great students will stay in the universities instead of going to the industry. No, but I agree. We need a lot of research work, and that is done greatly by this group. It's impressive, I have to say. I didn't expect it also. And as we said in the first meeting, that's top of the top. I want to add it and let them go out to the industry. Don't keep everything for yourself.
You will see, Peter, there are few people who really are at university after this exceptionally good master thesis. So we will talk to those students later on. So we'll see how many of them are in the industry and how many of them are at universities. Maybe it's time to switch to the first presenter. How we can start with that?
I make them co-host already.
Yes.
So I don't know if we have
the order of the people. One? Yeah, maybe the.
Alfonso is niet voor mij wel.
Yes. We start with Enrique, or what do you think, Frank?
Yeah, I think he's not there, or is he there?
I'm here. Yeah.
Yes, he's
okay.
here.
Excellent. You can start your presentation.
I don't know how to change this name.
What is his name?
Enrique.
Okay.
Hoe kan ik hem vinden? Want ik wil een presenter maken.
Ik heb hem nu gedaan. Heb je het gedaan? Ik denk het.
You need to let me share my presentation. I can.
Yes.
I already did.
So please try, Enrique.
Kan jij die melding nu op jou? Want jij bent de host.
No, okay. No, I can't. I still can't.
We have video control with you. Yeah. Okay, Enrique, maybe you can say a couple of words about you before you start.
Okay, my name is Henrique Gonçalves Afonso. I'm from Portugal. I'm 23 years old, and I'm here to present my investigation work on the design of high-strength steel standard plate eye girders and their combined NMV forces, shear force, bending force, and axial forces.
Okay. Are you at university after your master thesis, or you are in?
No. I'm working. I'm working now, actually.
Excellent. That's 1-0 to company. I think you can share your screen now.
Yeah.
That's right. Yeah. Okay. Okay.
Yes, it's coming up.
So, let's start.
Yes, please start.
Good afternoon, everybody. My name is Enrique, as I said before, and I'm here to present my investigation work on the design of high-strength steel standard plate eye girders and their combined shear, bending, and compression. So, to begin with, I would like to show which structures this verification is important, and this on structures like this one, in steel and composite steel concrete bridge decks, where apart from the normal bending moments and shear forces, there are also high compression levels on the deck. And as it is, it's important to check the NMV interaction. In the past few years, several studies have been carried out in order to improve the current formulations given by the Eurocode. I present you the Sinner-Beg and Jager and Kovesny studies, who studied the MV interaction, and more recently, Vizcaya, who studied NMV interaction and developed new formulations for unstiffened webs. So the main goals of my investigation were to evaluate the new formulations proposed by Andrei Vizcaya for high-strength steel plates longitudinally stiffened eye girders, and to evaluate the relevance of the longitudinal stiffeners in the structural behavior of these eye girders. So this is the current formulations given by the Eurocode. As you can see, we have these 3 parameters up here, which basically are the quotient between the applied forces and the resistant forces. And these are the equations that the formulations present us. And what did we find out? We find out that mainly because of this parameter over here, which is defined in 2 completely different ways, whether the web is fully compressed or not, the NMV interface surface has a discontinuity approximately to 45 degrees on the NM plane, which does not make much sense once we assume that the NMV surface should be something continuous and uniform. Once the numerical models show that. So this is the new proposal, the new equations proposed by Andrei Vizcaya. They are very similar to the ones that are present in the Eurocode, but they have new parameters like these 2, the reduced bending moment resistance of the effective section of the flanges, and the reduced shear stress resistance of the effective section of the flanges. This is a continue of the formulation. I didn't take part on the structure of these formulations. So to model my study, I pick up 20 cross sections of a total of 80, a sample of 20, defined by these parameters over here. So the slenderness of the web varying between 80 and 240, the height of the web established at 1 meter, the upper and lower length of the longitudinal stiffener at 100 millimeters and 50 millimeters, the stiffness rigidity established varying between 25 and 50, lower values, and the aspect ratio, which is the relation between the length of the panel and its side, varying between 1 and 2. That means I studied quadrangular and rectangular panels. To introduce the problem of the flanges and the contribution of the flanges in the problem, we defined 4 values for these ratio variables: AF, the area of the flanges; AW, the area of the web. So I had 20 sections, 4 ratios, gives a total of 80 sections that I studied on my investigation. So this is how I modeled the NMV surface. It was done with the spherical coordinate system, the formulation given by these equations here, with θ1 and θ2 varying between 0 and 90 degrees with intervals of 15 degrees. That means for me to have a complete surface, each surface for each section, I need to run 49 points of interaction for each one of these sections. That means for a total of 20 sections per ratio, with 4 ratios of areas, 49 interaction points gives a total of 3,920 NMV interaction runs in the numerical model software Abacus. This parameter, this R, is basically the norm, the distance between the origin, the point 0, to some interaction points. It's given by that expression. And it's important for you to know that we had some convergence problems, but they only represent 1.4% of the total sample, of the total NMV interactions that I did. And they were taken apart from the statistical study that I went through, so it does not have any impact on the final results. These are the final results of my investigation. So as you can see, in all the relation of areas, apart from the first one, we can observe that the new proposal gives better results in relation to the Eurocode. So this average is the value of the resistance of the numerical models dividing by the resistance of the proposal. and the average is always lower than the one obtained by the Eurocode. That means it's less conservative and more economical. In addition, we can also see that the standard deviation values are always lower for the case of the proposal, which indicates that there is much less dispersion of the results. It's a very more trustable proposal formulations. These are some graphics that I obtained in the final. So on the left we have the plots of the NMV interaction points obtained through Eurocode, and on the right we have the obtained by the new proposal, and it's clearly that there's much less dispersion on the results. Here are some graphics that I obtained. In blue, it's the proposal and the interaction points up. And as you can see, the NMV surface is not actually what is obtained by the Eurocode, the current formulations given by the Eurocode. So the main conclusions of my investigation: the Eurocode is very conservative, and that leads to a new NMV interaction proposal proposed by Vizcaya, as I said, which tends to be more reliable once it guarantees less dispersion of results, and it's more economical due to their lower conservatism. Thank you.
Yes. Thank you, Enrique.
You're welcome.
We have now opportunity to get some questions from jury. Is anybody interested to raise a question?
Yeah, maybe me again, because I think this is very interesting. I'm Peter, yeah. Because I think if it's allowed to use it, yeah, it's a direct result for our business, I have to say. This is one of the most important things we can get out of such works, yeah. So is there a possibility to get more information about this, or to stay in contact, or who will organize that the knowledge is spread over the world, let's say like that?
Will it result to adjusting the rules?
Yes. Enrique, do you want to answer that, or you expect an answer from me?
I didn't understand the question.
How this information will be disseminated to the new codes?
As I said, Andrei Vizcaya is developed these expressions, and he will present it to the persons who regulate the Eurocode, and they seem to be more economical. As I said, they are less conservative, and it gives us it gives us more economical results. We don't have to pay as much as now for the steel structures.
Yeah, maybe I can say to Peter that according to the new Eurocodes, which will be released in a couple of years from now, after the first major revision, it will be more promoted to use a high strength steel up to 700 S700 in the codes and standards. These are not fully fine-tuned rules, so I'm not 100% sure that specific results of Enrique master thesis will be directly implemented, but that will be certainly considered by the group of the people, the technical committee for high strength steel.
Okay.
Do we have
up to the TC, and I think there should be done something, yeah.
Of course.
Make some pressure. Make some pressure.
Of course, that is ongoing. Do we have any other specific questions to Enrique from?
Yeah. Hi, Milan. Can you hear me? It's Alan.
Yes, please go on, Alan.
Hi there. Peter stole my first question. I'm also interested to see these results find their way into the new Eurocodes, but we will see what happens there. My second question then was Alfonso's research had many thousands of theoretical calculations. I'm interested whether there has been any opportunity to test the theoretical calculations in practice with some practical calculations on full-sized beams.
Yeah, I didn't take part on that studies because mine was a master thesis, and his one is a PhD thesis. So he did actually some experimentally tests on eye girders with longitudinal stiffeners. Yeah, that's probably he will put that on his work, I guess.
Okay, thank you, Enrique, for your answer. We have maybe 1 minute for one more question.
Hi, Milan. Brian Huey.
Hi, Brian. Good evening, Brian.
Yes, good evening. Good morning. Yeah, good enough. Enrique, very nice work. I had a question, and I'm very interested in the area. Obviously, in Australia, we've introduced high-strength steel. So one of the things that intrigued me is in the initial application, you showed a cable stayed bridge, and you did show some shear connectors there. So any thoughts about how you could actually progress these calculations to use composite sections? Because obviously you would get the benefit of the concrete slab there being composite with the steel section. Is there any thoughts about that?
I'm not listening well. Could you repeat the question?
Sorry, okay, so my question was, in the initial drawing, you showed the application for the interaction between shear, bending, and axial force in the steel girder. And there were some shear connectors there, obviously, where the steel beam would be composite with a slab. So has there been any thoughts about, obviously, progressing this work where you would actually have a composite section? You could actually even further optimize these scenarios.
I don't listen well, but as I said, this can be used in steel composite cable stayed bridges. Once the longitudinal stiffener increases the rigidity of the web, so increases the rigidity of the web and automatically increases the resistance of itself to shear and compression and bending moments.
Okay, Enrique, thank you very much for your answer and for your question, Brian. I think we have to move on to the next presentation. Is Christian ready to upload his presentation?
Yeah. Hello, everyone, and welcome. My name is Christian Hilderda, and this is my presentation for the Dutch Open Student Steel Award 2021. Let me open my presentation. All right. So my thesis is about fatigue in tubular structures. It's about developing design tools that assist in analyzing and optimizing tubular structures that are subject to fatigue. The problem statement of my thesis. Fatigue is a material failure mechanism that occurs under cyclic loading. And there is a trend where it seems that fatigue assessment is becoming more important in structural engineering. For tubular structures, it is hard for an engineer to estimate the impact of his design choices on fatigue behavior. Let me highlight the second point that I said before. Why is this fatigue assessment becoming more important? There is more use of high-strength steels, but these steels often do not have a higher fatigue resistance. For the sustainability, there is lifetime extension of or reuse of steel members, and fatigue can be a limiting factor in this. And also optimization of welds, because welds are still a very costly process, but fatigue is often found in welds, so it's very important to understand what's going on before we can optimize this. Fatigue, it means that you're exhausted or tired. But for fatigue of materials, it means that under cyclic loads, such as wind or waves or traffic, there is microscopic damage happening in the material. And this can happen at even very low stress ranges. And this microscopic damage can accumulate into macroscopic damage, such as cracks that you see here, until possibly failure of your structure. As I said already, welds are a critical point in a structure with regard to fatigue. This is due to a number of things: weld imperfections, residual stresses, misalignment, and stress concentrations. And these all enhance crack growth and fatigue in the structure. So in order to avoid fatigue becoming a problem, we do fatigue assessment, which is calculating the risk that a structure fails due to fatigue and making sure that this risk is acceptably low for the required lifespan. I will discuss two ways of fatigue assessment. The first is the nominal stress method, and then the hotspot stress method. So nominal stress method. In structural engineering, we do this structural analysis to find deflections and stresses in the structure. And then we can do fatigue analysis. So if we want to, for example, find out what the fatigue life of this joint in the structure is, we can look in the norm. And we see a whole list with structural details, and each of them has a certain fatigue strength. We call this the detail category. For this joint, it would be category 40. And if we know the nominal stress, we can now calculate the fatigue life. So you could say that if I, for example, increase the wall thickness, this leads to a lower nominal stress and therefore a longer fatigue life. So that's in a nutshell the nominal stress method. So for tubular joints like this, there are many more design parameters, and you can say that the nominal stress method is not longer accurate enough. So we have to look at stress concentrations, and there are two types of stress concentrations. The first is the increase due to geometric discontinuity, and the second is increase due to the local weld geometry. And for the hotspot stress, we only look at the first. The hotspot stress is defined as the stress concentration factor times the nominal stress. And there are basically two ways of figuring out the hotspot stress. The first is by experimental methods, and the second is by finite element analysis. And years of research with these two methods have led to a set of analytical formulas, which look like this. And there are around 70 of these formulas, and they are all split up per joint type, load case, and position along the weld. And the inputs are these Greek letters, and they are called the dimensionless ratios. And they are a way of describing the geometry of the joint. So let me give this small example. On the right, you see a graph where I tried to capture the fatigue assessment with the hotspot stress in one figure. And if I increase the wall thickness of the big tube, as you can see on the left, then some things are happening. On the one hand, the dimensionless ratios change, so the stress concentration factor changes, but also the nominal stress changes, as we know. So the hotspot stress is affected in two ways, and the formulas are intertwined. So you can say that increasing the wall thickness, lower nominal stress, this is no longer true. So this makes it very hard to estimate the fatigue characteristics early in the design phase. And the result is that fatigue assessment is often performed after already many design choices are made. This can lead to higher costs due to late changes or the need to over-dimension the design to meet the requirements. Therefore, I made a couple of design tools with my thesis. The first is the fatigue design and assessment tool, and the second is Grasshopper. So first, the fatigue design and assessment tool. This is a tool made in Microsoft Excel with a lot of programming and macros going on in the background. And it basically consists of two environments. The first is the assessment environment. This is basically the engine of the tool. All the computations are happening here, and also the formulas are written out like in a report. On the front end, there is the design environment, which allows the user or the engineer to change his design until he is satisfied. And another part of the design environment are these graphs, which allow the user to relate certain inputs and outputs to each other to research how to optimize his joint. So concluding, this tool provides insight in the relation between inputs and outputs. It guides the engineer in which direction to change his design, and it has a written out fatigue assessment. So this is all verifiable, which is very important in structural engineering. Then let's move on to Grasshopper. This is a commercial software, and the way of working is called visual programming. It looks like this. A structure can be made by making dots and lines and connecting them with each other the way you want, and then structural members can be assigned to each line, and that's how you make a structure. And this is a parametric model, which means that each of the design parameters, as defined, can be changed anytime you want. The cool thing about Grasshopper is that it also contains the structural analysis. So loads can be put in the structure, and bending moments, nominal stresses, and deflections can be analyzed. In addition to the structural analysis, I programmed the fatigue assessment itself. So again, I used the stress concentration factors in order to calculate fatigue life. This is now possible in Grasshopper, and this has some great advantages because there is no need for other structural analysis software. There is a real-time fatigue life calculation per joint, and there is still the possibility to change the structure design, as you can see on the right. And because this is such a parametric tool, you can create many types of designs, not only towers, but also simple trusses like this. Okay, so that was it for the design tools. In my thesis, I performed a number of case studies, and I highlight the most important information right now. So I performed 2 case studies, created a total of 5 concepts, and this was all to test and verify the added value of the design tools. In the first case study, it all starts with the plan by the architect, and he gets to the structural engineer, which has to come up with an idea in order to make it all possible. And in this first case study, it was only possible for me to change the members. So I could no longer change the layout or the dimensions, only the members, diameter and wall thickness could be changed. For this, I used the fatigue design and assessment tool, and I calculated each of the nodes from the bottom to the top. And I eventually came up with a new concept. As you can see, only some members are changed. The initial design was already pretty good, but I managed to find some small improvements in there. And then the second case study. So now we have the same scenario, but as the structural engineer, we have more design freedom. So we can still make major changes if we want. So for this, I use Grasshopper because it's perfect for that. And I made a minor change to the geometry, and it has to do with the triangle in the middle that drives the shape. And it's changed, it's shifted up a little bit, 1 meter, and also the rotation is slightly increased or decreased basically. And this has led to a more efficient fatigue shape, you could say. So the goal of the optimization was to contain fatigue life of 50 years and optimize on the performances given below: weight, weld volume, and cost. In the first case study, it was possible to decrease the weight by 12%, weld volume by 37%, and cost by 16%. This already is quite good, but in the second case study, you can see that these results are almost doubled. So when we have more design freedom, we have more possibilities to create efficient designs. So the conclusion of my thesis. The developed design tools provide an engineer with very valuable insight in fatigue behavior of a structure already very early in the process. And the case studies have shown that with this approach, structures can be created that perform significantly better in terms of material usage and production labor. Recommendations. I would extend the tools for rectangular hollow sections. Right now, I only looked at circular sections, but there are also formulas available for rectangular sections. So I think this is very interesting. And also, I would advise to do research on a parametric design tool based on finite elements, so that also different kind of connections that do not consist of tubes can achieve such good results with regard to fatigue. So that was it. Thank you all for listening. And are there some questions?
Okay. Hello, Christian. Congratulations on your work and your presentation in 2 parts. Yes, as we saw. How long did you take to perform your thesis? Because the amount of work is really very extensive. So was this a 3-month thesis or a 1-year thesis?
I started in March last year, and I finished it in December last year. So you could say 3/4 of the year, almost a year. Yes.
So I have 2 questions that I would like to ask you. One, you have touched on, but what is your vision concerning the use of either low-level programming in tools like Grasshoppers and versus advanced simulation, let's say with Abacus, with Python, for example, as your as the way to make it parametric and fast and so on. And the second question is, how do you see, what are the challenges when benchmarking the level of safety when you use finite elements compared to code formulas?
All right, thank you. To get into the first question, I think that the low level of programming is a better way, or at least for me, it worked better because I'm not that much of a programmer myself. I really had to force myself doing this. And I think that if it's more reachable for a lot of engineers, then it gets more common for people. And I think that gains better results in total. And as you say, you have some very complex tools like Abacus, and you can perform very high-tech simulations, but also they take a lot of time. So it does not allow quick iterations. And that's really what makes the Grasshopper tool such a success, is that you can really quickly and easily make changes, go back one step and do it again. While in tools like Abacus, it just takes a lot of time. So that's the first question. The second question is, how do you benchmark safety with finite element methods, right? That's a good one. You have to see it as a complementary thing. You do not throw away the norms and everything that already exists. It's just a complementary thing to gain more insight and to gain more understanding of the problem. So it should work hand in hand, I think. But in the end, if you have a finite element approach, there are also a lot of regulations for that as well. So then I think, by adding them both together, you get the best end result.
Thank you very much. By the way, are you working already, or can we hire you?
I'm working already, so that makes it 2-0 for the industry.
All right.
Thank you, Luis, and for your interesting question. Do we have more questions?
I hope you work for steel industry and not concrete or wood.
Well, actually, I do kind of mixed things right now. I do also calculations on wood, and and concrete. But also steel is part of my job right now. Yes.
Okay.
Thank you for these unofficial questions. Do we have a technical question from a jury?
I have a question, Milan.
Please, Raffaele.
Hello, Christian.
Hello.
Also, from my side, congratulations for the excellent works and also for the nice presentation. Very, very impressive. My question is also in this case related to the vision for the future, no? And basically, I have seen that you have developed the design tools that is basically addressed to design new structure.
I have to hear that.
My question is you is if you think that in the future these tools can be also extended to existing structure, and in this case, if you have also some idea of if you have studied something concerning also the problem of fatigue when we have some damage due to corrosion, for example. So basically, my question to you is if you think that in the future a possible development of these tools could be also addressed to existing structure.
Mm-hmm. Thank you. Well, about the corrosion part, I knew of this problem, that corrosion can increase the speed of fatigue, but I chose to keep this out of my thesis because you have to put some limits on your problem. So I'm sorry, I cannot really give a useful answer to that. But about the existing structures is a very interesting question, I think, because basically what I did was make this tool based on an existing structure. This whole case study was based on a structure that is calculated by ABT already in 2013. Yes, it's kind of a reverse engineering what I did. And I think, yes, in the future, it could be used for existing structures. And I think right now of putting some extra materials or extra members in a structure, if that's a solution to stop fatigue, then you can you could model the existing structure and add some new components and still make parametric changes in that. That's something that I could see. But of course, yeah, once a structure exists, you can no longer change its geometry. So that may be hard. But yes, for reverse engineering, this tool can be very useful.
Thank you very much. And once again, congratulations.
Thank you.
Raffaele, now we are back in the Dutch landscape with the tulips and windmills. So this means our technique is working now. We have now to invite Paolo as the next speaker.
No time for question anymore?
I'm afraid that we have
to... no problem, no problem.
I apologize. Do we have a Paolo on? Yes. Paolo, are you ready to speak or? Just a second.
Okay, can you hear me?
Yes, excellent, Paolo. Please go on.
Okay. Good morning, everyone. I'm Paolo Capone from Italy, and I'm presenting my work about the behavior of metal forms and potentialities for application in floors of steel buildings. One second. Okay. So I'm going to say that, just 1 second, please. I have a problem. Okay. So the progress of the last century has been characterized by a severe environmental degradation, and most of all due to the production and consumption of non-recyclable products. Nowadays, one of the few chances to build our futures is to change this approach and develop new systems around the concept of sustainability and resilience, reducing the emission and guaranteeing 100% recyclability of the products. A great contribution to this situation of sustainability is provided by the construction market, accounting for the 40% of the CO2 emissions. It also represents a negative influence in terms of waste production, most of which with the limited use of materials at the end life. In the last 20 years, the attention to developing innovative, green, and optimized materials challenging the old generation has been great worldwide. And metal foams are one of the most noteworthy examples of the new generation materials, which are candidates for a significant advance of many areas of our societies in the direction of sustainability and resilience. 100% recyclable, they are developed around the concept of biomimetics, and despite their engineered nature, they provide features similar to many natural structures such as bones, honeycombs, or corals. Metal foams are created combining a gas phase with a metal in solid phase. And depending on production method, the gas phase provides a certain number of voids, leading to a drastic reduction of density without affecting the mechanical properties of the material. In fact, metal foams have higher stiffness to weight ratio compared to the solid metals. This characteristic results in a reduced consumption of material, making metal foams a great sustainability ally. Metal foams give significant benefits in terms of buckling mitigation and energy dissipation, providing a high shear resistance. This makes these cellular materials the ideal filling for monodimensional or bidimensional steel elements. And the range of practical application of metal foams in structural components is still negligible. Examples of use of metal foam can be observed in automotive, in transportation, mechanical engineering field, but there are not yet examples of structural application in civil engineering. Aiming to provide new solutions for the realization of new typologies of sustainable and low-weight structures, in my thesis it has been assessed the possibility to realize SAS sandwich panels with the steel skins and the high-performance aluminum foam core. My research work has been focused on the behavior in bending to investigate the possibility to use the panels on typical span of floor grids of steel buildings. The SAS panels have been realized with the two thin steel skins of 1.2 millimeters and an aluminum foam core of about 25 millimeters. Density of the core is 510 kilograms per cubic meter. It is bonded to steel skins testing multiple epoxy binders solutions. The aluminum foam used to realize the panels is produced by Cymat Technologies in Canada. To fully understand the capabilities of this material, an experimental campaign on metal foam and SAS panels has been set up. In the first step, tests have been performed only on the aluminum foam in parallel and transverse compression. The material has two different values of resistance and elastic modules in the two main directions. It is higher in foaming direction rather than in transverse direction due to the lamination process that deforms the voids of the external layers of the aluminum foam panel. The most interesting thing of these tests is the absence of a degradation phase for the material in compression. In fact, the foam achieves a plastic strain of about 0.9 without any loss of resistance. The second step of the experimental activity has regarded the shear and bending test only on the aluminum foam. 3-point bending test and shear tests have been executed varying the point of application of the force. To assess the displacement of the specimen, three laser transducers have been installed, and two string gauge for each side. And this is the results of the 3-point bending test on the aluminum foam. The results of the test can be visualized on the diagrams, and they show a yield point of about 20 megapascals and a bending modulus of about 10,000 megapascals. In the third and last step, it has been assessed the performance of SAS sandwich panels in bending. The assembled panel has reached a bending moment of about 1 kN, which, considering that tested as a width of 75 millimeters, referring to an equivalent panel of 1 meter width, the corresponding bending strength would be of about 14 kN. After a displacement of about 20 millimeters, the specimen lost almost completely the resistance to the buckling of compressed top skin. Then an analytical modeling phase has been performed, adopting simple elastic and plastic modeling approaches to predict strength and stiffness. And here follows a quick presentation of the results, starting from with the stiffness of those SAS panels and then with the yield strength for both steel and foam of the sandwich panel. Then using the stress strain curve for steel and foam, the maximum bending moment resistance has been calculated. Additionally, starting from bending moment curvature relation, a step-by-step numerical procedures have been set up to model the force displacement curve. The main results of the analytical modeling has been that simple analytical equations can be easily applied to predict stiffness and bending strength of the panels. And we can see that step-by-step modeling has also a good match with the experimental results. The obtained results of the experimental campaign have been used to develop a finite element modeling using the software Abacus. Two elements have been defined and geometrically modeled. The first one are the steel skins, and the second one is the aluminum foam core. The model has been performed considering both the elastic and plastic behavior of the materials using the data from the experimental tests, and so defining a Young module and Poisson ratio for elastic properties, while yield stress and plastic strain have been defined for the plastic behavior. Only for the aluminum foam, a damage law has been defined, providing the damage initiation point and its evolution, and then the contact between skin and core has been defined with a cohesive behavior, where the required parameters are the stiffness in 3 directions, the damage initiation stress, and the damage evolution. And we can see the results of the finite element modeling with a perfect overlap, quite perfect overlap with the experimental ones. The calibrated numerical model have been then extended to perform a parametric study. All the parameters affecting the response of the panel have been alternately changed to obtain 50 numerical analyses. The parametric study shows that the stiffness and resistance for the panels, also considering different geometries, can be easily controlled through simple design equations. The resistance linearly depends on the panel skin thickness and the strength of the steel skin. The adhesive controls the ductility, and a high ductility can be obtained only if the adhesive is able to avoid the occurrence of local buckling phenomena. This objective can be achieved only adopting adhesives with a high resistance. In our cases, at least 7.5 megapascals. Regarding the foam density, literature equations have been used to model cases with density lower than 110 kilogram per cubic meter. The foam controls the shear failure of the sandwich panel. The numerical results indicate that the possibility to adopt lower density foams for the application of the SAS panels in floor. The most interesting thing confirmed by both the numerical and analytical modeling is that it would be possible to reduce the density to a value around 100 kilogram per cubic meter. A case study comparing two solutions, the first one with a typical steel concrete composite floor and the second one with the SAS panel, demonstrates that it is possible to obtain a reduction of 85% of the self-weight of the floor, while a reduction of weight up to 20% on the entire structure. Mass reductions means reduction of gravity and seismic loads, resulting in a size reduction of the load-bearing elements as well as the foundational structures. Once again, so with a reduction of materials and more sustainability. In conclusion, this solution may provide significant benefits in many ways. First of all, the structural lightness with the reduction of floor weight and the entire structure. Benefits are clearly visible on safety and speed of installation because the SAS panel is a load-bearing element and it doesn't need a cast-in-place concrete. And for the same reason, this structural solution is dry assembled and 100% deconstructible. And at last, the costs are competitive compared to those of typical solutions, but with the sizing reduction of load-bearing elements, cost benefits are visible on the entire structure. Thanks for your attention.
Thank you very much, Paolo. Now we have a time for questions.
Hi, can I ask a question?
Yeah, please go on.
Yeah. Hello, Paolo.
Hello.
Thank you for your nice presentation. I'm Gang Xu from Tsinghua University, China. So I have two questions. The first one is, how long a time does it take for your master research work? And the second one is, when you simulate the core, the foam, what element did you use? Thank you. That's all.
Yeah, thank you for the question. So for my research work, I studied for 6 or 7 months, about 7 months, and the second question is about the foam core.
Yeah.
The modeling in finite element analysis has been I used the an elastic behavior for the panel, and the required parameters are that of the experimental data. So for the density, we used the density of the panel. The plastic behavior and the damage law has been maybe I not understand the question well.
Okay, thank you for
No,
your answer.
I have a question, if I may.
Okay, I'm sorry for my English first, because I'm not so practical.
Don't worry, Paolo. We have a next question.
Okay.
Yes, Paolo, your research is very interesting, as you took the idea from nature, which is always inspiring. So the bulb of a ship is in the end taken from a dolphin. So I like the idea. What my question to you is, to me, getting the cellular structure into profiles, into plate, into the material looks in practical terms to me very, very challenging, and if we ever want to use this idea, I think there should be a real producer that produces such material. Have you taken into consideration, have you talked to people familiar to this type of industry, and can you tell me something about the let's say the practicality of to get to the material you're proposing?
To use the metal form to feel the feeling, like feeling in the steel elements.
Yes.
Okay. Yeah. My research work is about the assembling of a sandwich panel, which not required the infilling of the metal foam in the steel profile. So we have assembled the panel with the epoxy binders. So the panel, the foam panel is just produced by is just taken and assembled in a sandwich panel. So we not have to infill some the steel profile. So we have not investigated this aspect.
Thank you, Paolo. Maybe we have some industrial partners in
the it's Olivier, if I may.
Yes,
so
please, Olivier.
In fact, we had some years ago the same reflection about foam glass, because here you use aluminum foam, metallic foam. We made the same reflection with foam glass, and as you said, to cast the foam into a tube or something like that, it's a it was a too big challenge in a sense. So we worked like you on sandwich panels, but with foam glass. Did you look at a comparison when you made your literature study? Did you look also at what could be achieved with foam glass compared with aluminium, as you said, and what is the difference in performance?
No, we used the literature only to change the parameters of a density, a lower density foam. So to extract the young models of for example the 200 and 100 kilogram per meter per cubic meter of the foam. So we not investigated the alternatives of other new materials.
Yeah, thank you very much, Paolo. We have to move on.
We have seen the chat.
Yes, do we have?
There's in the chat.
Yes, but do we have time for that?
No, it's very short. So
yes,
somebody will give a good price for this aluminium foam.
Okay, but that's very interesting.
Norbert.
Yes.
Brescan.
Yeah, very good. There is this is not only ceremony, award ceremony, but also a matchmaking site. So it's very good. Thank you for this input. We have to move on with Olivier's presentation.
Yes.
Are you ready, Olivier?
Yes.
Please share your screen and
where is it?
We are ready to your talk.
Okay, can you see my screen?
It's coming.
Yeah. Started to share.
Excellent.
So you have it?
Yes, perfect.
Okay, so yeah, I'm really happy first to have been, I would say, working in this jury. So as you know, I'm sit between two chairs, in a sense that I'm sitting the chair of the professor of steel structure and the industrial chair at ArcelorMittal. And I'm really happy when such meetings are organized, because it makes really the link between the industry and the academic world. So today I will talk about the sustainable future of steel. It's a quite, I would say, really large topic. But what we see clearly is that climate emergency is really something which is accelerating. We saw since the Paris Agreement in 2015 that we really changed. The world in Europe really changed. We had a lot of demonstration. We see the new generation which is on the street to push. Milan, if you could put you on mute, if possible. because there is a lot of noise coming from your side.
I will check that with our staff.
Or not move. Thank you.
Yeah.
So there is a clear acceleration of the public, really the people, the people in Europe on this emergency. So as a steel industry, we need to do something. So what we have started is that we have started a quite massive action plan to decarbonize steel production. So what I will show you, it's what we do, but I would say there are many competitors which are also working in the same direction. We have also competitors which are working with us into this direction, into common projects. So here it's I would say, project that ArcelorMittal has put in place, but it's things that the steel industry will do. So first of all, we took 2 ambitious targets. The first one is to decrease in Europe by 30% our carbon emission by 2030. So at industrial scale, 2030, it's tomorrow, because to decrease by 30%, it's a massive amount of things that we need to do. And we are working on 3 different streams to decarbonize the industry. And then the second target we put as a company, it's to be carbon neutral by 2050. So again, to pass from 2 tons of CO2 per ton of steel to carbon neutral in 2050, the road is quite long. So where are we working? We work in all the steps of our production route. So what I will highlight here is some of the projects we already put in place. So what I show you here, it's not, in a sense, research and development anymore. We are reaching the industrial scale. So we are now building in our facilities industrial pilots to apply these technologies. So you have here the blast furnace. And what we do is that we look at everything which is possible to technically reduce the CO2 in the blast furnace, or to decrease the carbon input, or to do something with the carbon we emit. The first project, which is now under implementation into Ghent mill in Belgium, is to replace the coal. So a big part of the CO2 which is emitted by the blast furnace is coming from the coal. So what we do is that we put at industrial scale a mill which is from waste and biomass generating biocoal. So we are gathering plastics, waste of wood, that we will torrefy. So we will create charcoal with it, and this biocoal will be injected into the blast furnace to replace coal. So this will allow us to decrease at the end the carbon footprint of the blast furnace. That's one of the projects. The second one, and you saw probably some pictures on the social network about this, it's a technology which is called Carbalyst. So it's a technology which is capturing the CO, the gas, which is going out of the blast furnace, we realize a first gas treatment to cool it down. And then we created with Lanzatech, which is an external partner, a bioreactor. So in fact, these gases are mainly based on CO and CO2. So what we use is that we use alga. So I would say algae, it's like vegetables, I want to say, that will digest the CO2. And digesting this CO2, they will emit and create ethanol. So at the end of the day, we have the gas which are going out. They are treated by this bioreactor, and the bioreactor is emitting ethanol and biomass. This biomass is going back here as torrefaction and is injected again into the blast furnace. And then with this ethanol, we can deliver it on the market as alternative fuel, as product to fabricate some plastic or some chemicals. A third one, because we know that at the end of the day, we will have a remaining CO2 emission. So we are also working on what we call carbon capture. It means that with the remaining CO2, we develop technologies to capture the carbon and being able to transport it and store it somewhere. That's something they use a lot in countries where they produce oil. To produce oil, you need to inject gas in the earth to have the oil going out. But what they can do is to inject CO2. The CO2 is heavier than the air. So as soon as it's injected in the ground, it stays in the ground. So we will, with this CO2, they will not inject air anymore in all these type of industry, but they will inject CO2. That's what we call the carbon capture and storage. So that's what we do at industrial scale into the blast furnace today. But we know that to reach carbon neutrality, that will not be sufficient. We need to rethink the way we produce steel. And the alternative to produce steel compared to the blast furnace is the DRI route, direct reduction iron. In fact, a DRI is, I would say, a tower like the blast furnace, but you only inject ore. You don't put coal. So you just put the ore. And today, with natural gases, you do the reduction of the iron ore into HBI, so into steel. What we are developing in Hamburg, and again there we reach the industrial scale, is that we don't inject any more natural gas, but we inject H2, hydrogen. So in the future, and massive investments are realized by European Commission on this, in the future, we will be able to get CO2-free hydrogen. Hydrogen that will be produced from renewable sources. So if in this system you inject CO2-free hydrogen, you produced CO2-free steel. So that's where we are today in terms of industrial development and industrial roadmap. But don't forget, steel you don't use it only once. The beauty of steel is that it is recycled again, again, and again. So we need to continue as designer, as steel user, to gather the steel and recycle it. And us, as an industry, we need also to do our homework to recycle this steel in the most efficient manner. So what have we done so far? And that's something we launched some weeks ago only. It's the ability to produce recycled steel, but with 100% renewable electricity. It means that when you recycle steel, your main source of CO2, it's the CO2 which is emitted to produce the electricity. And if you can guarantee that this electricity has been produced with renewable sources like solar and windmills, and that you feed all the steps of the production with this green electricity, you see that the carbon footprint of the steel is really low. It's as low as 0.3 tons of CO2 per tons of finished steel. So that's the other axis that we are working on, and we are live today on this. It's the ability to produce and to recycle this steel from renewable electricity. So that's where we are today, and that's where I end my presentation about the future of production of steel.
Okay. Thank you very much, Olivier, for your presentation. Are there any comments from the audience or from the jury?
12 points. 12 points.
Please, please.
I was awarding 12 points to Olivier.
Thank you.
Maybe we go on with the next presenter, Andreas.
Can everyone see my screen? And
yes.
Hear me? It's maybe the more important question also.
Yeah, we can hear you and we can see your screen.
Very good. Then I would like to start my presentation. First of all, I would like to thank you very much for this opportunity to join you in this jury for this very important, beautiful, and interesting award. I think this was a really great idea that the Dutch side decided to open the competition also to the rest of Europe, and it's a very nice event with very interesting presentations that we have seen and we're going to see. So it's a pleasure to be part of it. My name is Andreas Thalas. I'm the professor of steel and composite structures at ETH Zurich. I started here at the end of 2019. So like everyone, we all had a quite interesting year 2020. If you ask me a little bit about the city of Zurich, I cannot tell you too much yet because we were, like everyone, locked in our houses. But I can tell you a little bit what is going on in steel research at ETH and a bit with this presentation, my view of what will come in the next years for steel construction. So besides the many interesting things that we are going to see in this award, I just want to talk about some technologies that I think will really change how we do steel construction, steel design particularly, and steel construction in the future. Partly topics that you mentioned as well, the students mentioned, we go a little bit into that, and partly some additional points. So a look ahead, where do I see us headed? I think that these new technologies that will be further developed and brought to market by the young, bright minds that we are meeting today will definitely change how we carry out structural steel design and engineering. And therefore, the main goal, I think, of all this should be that it should unleash the creative potential of our field. Right now, we're often, especially as engineers, burdened by the many verifications, for example, that we have to do when we design something. And we have a little bit abandoned the field of creativity to our friends from architecture. I think there are, at the moment, quite a few things going on that will allow us to go back to the roots, actually, of our profession, which is essentially a creative profession. So I think, just to give 2 sentences, the future will entail fewer formula and checks. There will be much more design in the original sense of the word, and creativity for structural engineers. And on the side of the construction, I think for some years now, there has been this buzzword, this catchphrase, design for fabrication. Let's design things and thinking always, how can they fabricate it, and make, let's avoid designs that are not cannot be fabricated easily. Certainly this will remain important, but I see many trends where the opposite will also become more important again. So fabrication will be more and more be able to be made really bespoke for the design wishes and for the construction projects. So there will be more bespoke fabrication that allows us to design more efficiently. So let me just briefly review how we design traditionally. So even at the moment right now, we have really fantastic codes in steel construction, much better than in any other field. Decades of hundreds of researchers that have put a lot of intellect into creating these very good design rules that we have. But still, if we take the example of compression member or bending members here, there are some things that inevitably are a little bit inaccurate and lead to what I was mentioning before, this rough and complicated design. So in one part, we need to classify the behavior, which can be quite diverse, of our structures and structural members. So we all know this classification system that we use, by which we classify the formation capacity. Strength is estimated by functions like the one we see here. We assume certain things about how stresses are distributed. This leads then to certain formulae. Then, for example, instability is then represented by a set of formulae that was developed by tests, many statistical evaluations. This gives us such functions that we then use. And everything is based on the assumption that everything is done just as well as can possibly, as is the minimum that is required, let's say. So we use low frac tests for material parameters, for what production will do, geometry, and so on. This automatically leads to, even in steel structures, leads to an underestimation of strength in the range of 20 to 50% in many cases. Other cases could even be worse. What can we learn, though, from tests? So many of us are at universities. The master theses were developed there. There were huge advances in the last years in how we can test things and how we understand tests. Some professors that are more veteran than me have told me sentences of the type, I wish I could go back with the new testing equipment I have to what I was doing when I was a PhD student. Everything could be repeated now. We understand so much more. So that is certainly true. These days, we can measure much more about what we test. Instead of a few strain gauges, a few LVDTs, we can, for example, observe a stress field and deformation field in a buckling test perfectly. We can, with 3D scanning techniques, really know what was our specimen before we tested it. And of course, we still have the traditional methods to assess strength and so on. One of the main things that I think is really giving us much more insight is what you see here in these little videos, even just for a tensile bar, how are strains distributed. With DIC, we can really not only see geometry, but really see where do the stresses go, how do cracks grow, many things of this kind. So we really can gain a lot of insights from more testing. So to the company people here, I can only say, come back to us at university. We could learn so much more from tests. The same can be said, that was large scale. We can say it of smaller scale things. These are, for example, some 3D printed bars. We can really go into the minute geometry of these bars and learn what do they look like, and therefore then use it to see how they perform. Can we replicate these things in simulations? The quick answer, because we're short on time, is yes. Today, if we simulate, if we take all the knowledge that we gather in these tests and simulate it, we can tell you exactly how these elements will perform. Not everything as precise as I'm showing it here, but many fields, plastic fracture and tensile bars, for example, or the buckling performance of slender high-strength steel elements like shown here. On average, we can simulate, if we gather this information, we can say exactly, or to a very, with a very low scatter and high precision, what will be the strength of such elements. So also here, huge advantages were made and are still happening. Can we use any of this? I can for sure say that the Eurocodes are, as always, very modern codes, and in the next generation on which many of us are working, and many of the things that are being developed also in these master theses will end up in the Eurocodes. We are quite advanced compared to other continents also. There is now a code under development that will allow us to use much of these advances in simulation also in daily design, much more. So don't focus too much on the figures. I know they are very colorful figures, but they should show in design, we will get away from all these formulae for sure, and use much more of this accuracy that we have in simulation also in design. But I want to talk about maybe another aspect where I see us heading, which is artificial intelligence. We use it all over the place. I think this will really inform our prediction models much more and more in the future. We are working on this. Many people are working on this. And just to show you an example, I showed like these thin-walled structures before. You have here slenderness. Here, this audience understands what this is about. You would have here resistance compared to a Eurocode resistance. So one would be, where do we design? This is the capacity of a cross-section. Right now, we have this mess, let me call it a little bit, this big cloud here with the 50% inaccuracy, up to 50% that I mentioned. We did a project at my former university with many partners, a European RFCS project, where we used really I believe our human intelligence. We really squeezed it as much as we could. And from this, we got from here to here. And I think in many things, we were them better. But still, you could say there's still big scatter, things of this type. And then lately, we try to use artificial intelligence on all these thousands of numerical results and tests that we carried out. And here, the big thing is that one needs to look at this scale here. So the same results with the application, in this case, of a deep neural network that understands what is happening now, there is almost no more scatter anymore. So we have a formula that if I printed it out, it would be 2 pages long, but that doesn't matter today. That was developed through artificial intelligence, and that can tell us exactly what or with a minimal scatter still, what the strength of these elements will be plotted over this slenderness. So these testing techniques lead to a much deeper understanding of structural behavior. With this, we can do excellent simulations that we can then see as numerical tests. So we can create thousands and thousands of tests. And if we then couple this with AI, like this little example here, we really become super accurate in our designs. What will change in fabrication? Just briefly, I really see this 3D printing technology, which was present also in many applications, in many submissions to this award, as really the key that will change assembly of steel structures. So certainly we're not the only ones working on this. I'm showing some photos that were much seen and observed in practice in the last years. I don't want to say too much because I'm sure the next presentation will also talk about it. And this last presentation also said something about the green future of steel. I really believe that recycling, use of renewables, also this hydrogen technology will make steel very central to a green future. But one aspect that maybe wasn't mentioned so much, it's really observable that steel makers are more and more able to give us plate material, bars, much more as specified by client. This is done in other disciplines much more than in construction, but can be done, will be done much more. So we can really go away from assuming that we get the worst possible plate, especially if we go to modern steel fabricators that we have on our continent. Then let me just finish with some last sentences. I think it's once again a great time to be studying steel, its structural applications and their design and performance. It's really noticeable in Europe that there has been a push for new steel construction, both in architecturally minded structures, in big infrastructure projects, where there once was a concrete bridge, there is now a steel bridge. I just want to point out the potential of this endlessly recyclable material is really being recognized more and more. In some countries more, in some less, but in general, I would say in Europe, more and more builders, authorities, and infrastructure owners recognize this. These new technologies developed by these young researchers will allow us to keep this momentum going more and more. The prerequisite is the clients, owners must recognize this. They really must want in construction to try something new. This is where it sometimes is lacking in construction. But even more, the building authorities have to go along with this. And with this, I would like to thank you, and I cannot not use this opportunity. And we, of course, welcome any contact from all of you. Thank you.
Thank you very much, Andreas, for your inspiring presentation. I really appreciate your efforts to put everything together. Do you have any comments, short comments? We are a little bit behind the schedule, but it is always nice to hear a comment or two.
Yeah, it's Olivier. It's more a general comment. So here I will take my head of industrial, and you presented that we have the best norms which allow us to, I would say, to calculate really well. In a sense, I agree. And we see a lot of developments coming in the codes and so on. But where I disagree is that globally, we have now numerical tools, and you show them also, that can, with finite element, with artificial intelligence and things like this, do really advanced design. So why do we need to spend time and energy to have really complex things as an analytical procedure in the code, which makes life of steel fabricator, life of engineering office quite complex, because it becomes really complex if you want to optimize. If on the other side, you have all these numerical things which are popping up. So simplify the code, make it easy, simple, not optimum, of course, and then allow the use of numerical things for optimization. But we try to bridge the gap with the analytical, and that, for me, I don't know if it's the best tendency, but it's more philosophical than anything else. But
I don't think we disagree. I think I was saying the same thing, but
yes,
I was saying the same thing. I was saying that we have pretty good codes compared to concrete already, but we are gonna move forward just like you suggested.
Yeah. Thank you, Andreas and Olivier, for this short discussion. I think we have to go on with Ben. Of course, we will discuss these issues much more in days to come. But now we have to finish the ceremony award. So Ben, please, are you ready?
Yeah, sure.
Excellent.
You should be able to see my presentation, I hope.
Yes, correctly. Please go on, Ben.
So, hello everyone. My name is Ben Weber, and I'm presenting my master thesis on the material anisotropy in wire and arc additively manufactured structures. This was a 3-month project at Imperial College London, and I subsequently started my PhD in Professor Gardner's group because I liked to continue my research on this. So additive manufacturing and construction is certainly a major player in Industry 4.0, the next industrial revolution where we are in the middle of. However, until now, there has not been a really widespread utilization in the construction industry of additive manufacturing, mainly due to the difficulty of assessing the safety and reliability of the structures. This comes from a major part due to the lack of fundamental understanding of the underlying materials, as the data is really scarce at the moment. Today, I want to talk about VAM. What is VAM? VAM is a specific additive manufacturing procedure, which is called wire and arc additive manufacturing. In our case, we are studying VAM using stainless steel. VAM allows for printed structures of nearly any desired geometry and size, with a relatively high deposition rate of up to 9 kilograms per hour per robot, but multiple robots are definitely possible. This further increases the speed with which a structure can be produced, thus allowing for industrial-sized structures to be produced in a reasonable amount of time. How does VAM work? VAM essentially is a welding torch mounted to a robotic arm that can move the welding torch in 3D space. The torch melts down a wire stock, in our case stainless steel, and puts it down in a layer upon layer fashion to create the 3D objects. Some benefits for VAM that are also present in many other additive manufacturing procedures is that VAM allows for lighter and stronger structures to be produced through the utilization of topology optimization. This reduces material, it reduces production time, thus reducing costs. Additionally, VAM is also able to be used in situ production, where, for example, larger structures could be produced on the construction site, removing the necessity to move large structures over our road networks, or even construct structures that are much larger than possible to be transported. Also, VAM allows for a new architectural and design freedoms for the architects and engineers, because it allows for new structures that would not have been possible before to be considered, or even structures that would have been possible but just prohibitively expensive to be produced in a reasonable amount of money and time. So how do we want to help assessing these structures? Well, we started with tensile coupon tests. Tensile coupon tests of different materials in VAM. This means we had different surface finishes, one as built, one surface finish machined, which means that the surface undulations that are present due to the additive manufacturing step have been removed with an end mill. Different thicknesses were also tested, namely 3.5 and 8 millimeters. To get an idea how the VAM material behaves in different orientations, we cut tensile coupons from different orientations of the same sheet metal, printed using VAM. A 0-degree coupon means that the deposition direction is parallel to the tensile direction of our tensile coupons, and then relatively for the 45 and 90-degree directions. Measurement of our tests was done using DIC, digital image correlation, with a 4-camera setup. Why a 4-camera setup? So we were able to measure both sides of the coupon, and also a stereoscopic image, which in the end led us to measure not only longitudinal and lateral strains, but also through thickness strains of the coupons. From the raw data from these tests, which you can see, for example, on the right-hand side for longitudinal strain graphs, we can also already get a qualitative assessment of the material behavior. And you can clearly see that the strain plots are not the same for the 3 directions. And there's a clear 45-degree inclined strain field, for example, in the 45-degree coupon. So this already gives us an indication that the material doesn't behave in an isotropic way anymore. Looking at the stress strain graphs of the same coupon tests, this anisotropic behavior manifests itself again, where the three different directions behave vastly different from each other. So we can't really utilize a normal isotropic material model that would be the initial assumption for steel structures. So upon research, we came up with a planar orthotropic material model that fits our material behavior best. Essentially a planar model because our structures are relatively thin compared to their longitudinal and lateral directions. So we were able to use shell elements in simulation. This model consists of 4 independent parameters, 2 Young's moduli in the 0 and 9-degree direction, Poisson's ratio and shear modulus. This work focused mainly on the Poisson's ratio, but also determined the shear modulus, because the shear modulus is really difficult to measure directly. So we found a relation between the different Poisson's ratio Young's moduli to get the shear modulus, where essentially you need a measurement at 45 degrees. That's also why we did this measurement of our coupons. Why Poisson's ratio? Well, the Poisson's ratio essentially gives us the lateral behavior of our material when it's stretched in its longitudinal direction. And we take, in our definition, the local slope of the transverse to the longitudinal strain graph. Because the model is really linear in the elastic range, we were able to represent the Poisson's ratios with a single value for our coupons. Coming to some results. For the elastic Poisson's ratio for the 8mm machine coupons, you can see that they are rather similar for the 0 and the 90-degree direction, but vastly different for the 45-degree direction, which again comes from the orthotropic material behavior. We can predict how this one would behave with theoretical curves that are fitted to the Young's modulus, Young's moduli evolution over the different off-axis loading angles. So in the blue thick curve, you can see how EX and EY are evaluating over the different angles. From this, we can then determine how the Poisson's ratio would evolve. However, it needs to be stated here that the Poisson's ratio model is only fitted to the 0 and the 90-degree directions. Thus, the 45-degree direction is not fitting to this model, but it lays very close on the line, which further validates that our orthotropic material model is correct. As an indication, we also investigate how the shear modulus would behave, and you can also clearly see that shear modulus is varying by quite a lot over the different off-axis loading angles. However, the elastic material model is not sufficient to get a clear simulation of the material behavior. We also need the plastic behavior of our material. A first analysis was done for the plastic Poisson's ratios, which against the assumption of a plastic Poisson's ratio of 0.5 for steel are varying over the different over the longitudinal strains, and there's also clear distinction between the 0 and 90-degree and the 45-degree direction. But this varying plastic Poisson's ratios can also be seen in other orthotropic materials, such as orthotropic aluminum sheet metal, where it has been detected as well. Another important part for the plastic analysis is material yielding. So from, let's say, isotropic materials, the von Mises yield criterion is often used, but this one is not longer valid for anisotropic materials, where the Hills yield criterion can be utilized. Hills yield criterion essentially adapts the von Mises yield criterion with Rij factors, which essentially fit it to the anisotropic material behavior. These Rij factors can be determined using stress ratios, and you can see the results below for the machine coupons. Looking at how this changes our yield surfaces, in orange, the von Mises yield surface, and you can clearly see that the Hills yield surface for the anisotropic material has been skewed to the new parts. And this is due to the R factors that are introduced in the Hills criterion. Where does this all lead to? Well, the results from this thesis were utilized in the FE analysis of the MX 3D bridge, the world's first metal 3D printed bridge, where the FE model didn't line up with the test results before with an isotropic material model. But after utilizing the orthotropic planar material model that was presented here and the stress ratios with the Hills criterion, you can see, for example, on the right-hand side that the mid-span bending moment and mid-span deflections are lining up really well between the test and the FE analysis. I would like to give a short outlook. So currently this research has been put into a paper and has been accepted for Eurosteel 2021 called Characterization of the Anisotropic Response of Wire and Arc Additively Manufactured Stainless Steel. And we are currently looking into verifying our plastic material model in FE and also evaluating the whole model using CHS and SHS stub columns to see if it is robust in more applications than the ones that have been analyzed so far. Lastly, we also want to look into optimizing not only the topology of the structures, but also the material orientation in those structures to take the most benefit out of the additively manufactured structures. I would like to thank my supervisors, Professor Gardner and Dr. Hadjib-Metalis, for their amazing support, and would like to thank you for your attention.
Many thanks, Ben, for your presentation. And we have a couple of minutes for the jury questions. Are there any questions from jury on this presentation, please?
Yes, Milan, can I ask a question?
Please, Luis.
So, Ben, first, congratulations on your work and helping recover 2-1. Italy is, of course, in other football leagues, so we don't count them. I have two questions, one more general and one more specific. I'll start with the specific, and it relates to the fact that you mentioned nothing about the true thickness properties of your samples. So reflections on that. And the more general one relates to the 3D printing process. You receive your samples directly from MX3D, but the 3D printing process is really crucial, because what will happen is that in the future we'll have bespoke properties also from the way we control the printing process. So also I would like to hear your views on this. You did not mention about digital twins that are of course essential to really have economy and productivity in this process.
Yeah, sure. Thank you very much for your question. So for the through thickness directions, yeah, that's a good point. Definitely we have analyzed it, and because DIC is not really has not the best resolution in the through thickness direction, it was rather noisy, the results. But however, you can see, for example, here where we analyzed the constant volume of our or the volume of our coupons using the 3 strains and to check if constant volume is still fulfilled. And you can essentially see that the through thickness measurements were stable enough to see that the constant volume is more or less conserved over the whole longitudinal strains. To maybe indicate a little bit more, in the elastic domain, the through thickness measurements were too noisy, so there's a very big signal to noise ratio in this domain. So in the elastic domain, it was not really usable, but for the plastic domains, we were able to get reasonable results. For example, you can see here the dashed lines on the bottom are the 0-degree direction Poisson's ratio in the through thickness direction. So you can we were still able to get reasonable results out of it. Coming to your second question, I think, yeah, that's a very good point. 3D printing is really dependent on the production procedure you're using, on the specific welder you're using, on this, maybe it's specific material you're using, the specific gas, feed rate, and so on. Our group is currently also researching in this direction, but the results have not been published yet. However, I think it just needs some by Eurocode or by some other agency a standardization process, as we have also for other steels, where we say, okay, an S275 steel is an S275 steel. So you just need a process where you're saying, okay, this stainless arm fits in this category of strength, this is in this category of strength. And when you have this categorization that is not too complicated, then it will make the design for the engineers much easier. However, for more specific designs, you could always do tensile tests, as we did here, specific ones for the specific application if the steel doesn't fit your design directly.
Thank you very much, Ben. We are really short in time, so I think we have to be happy with those questions from Luis and your answers. We have to move on to next presenter in order to keep, to some extent, our original plan. Just one comment. I think you stay at university, so it's a 3-1 company to university.
Yeah,
so far.
Exactly.
Thank you. Angeliki, are you with us and are you ready with your presentation?
You're gonna tell me if I'm ready once I'm gonna start sharing my screen.
Yes.
Can you see everything? Perfect.
Excellent. Please go on.
Nice. First of all, I want to say that if someone would have told me a year ago that I will be here today, I wouldn't believe them. A year ago, I got my master's degree from TU Delft. On the day of graduation, I had to present my thesis project. You can actually see how the cover of my thesis looked like. It's on the left-hand side of your screens. For a year, I was busy with following an experimental and numerical approach to investigate possible ways to connect a GFRP tower with a steel support structure for offshore wind turbines. And although I spent a year on this, today I'm gonna have to squeeze everything into 9.5 minutes. And to do so, I'm gonna follow a very basic format. I will start by presenting the motivation that led to the problem statement, then the solutions that I propose to fix the problem, some results, and of course, the conclusions of my research. Before I start doing this, I want to address the elephant in the room called the GFRP. It is mentioned in the title, and I'm not so sure if everybody that participates in this webinar knows what this abbreviation means. So I want to elaborate a bit on that. GFRP stands for glass fiber reinforced polymer, and it is a composite material. The term composite material is used to describe every structural material that consists of two or more constituents that are combined at a macroscopic level and they are not soluble in each other. GFRP is by far the most widely used material in commercial composite application. And the two ingredients are the fibers, and these are surrounded by the polymeric resin, which is also referred to as the matrix. So the matrix has 4 roles. The first one is to fix the fibers in the desired geometrical arrangements. The second is to transfer the forces to and between the fibers, to prevent them from buckling and to protect them from environmental effects. Of course, the fibers provide the dominant load-bearing function and stiffness of the material. But the question is, what is the story behind my topic? So Joulstock is a company that develops GFRP tower structures with the aim to replace the current steel towers. They claim that this will reduce the cost of an offshore wind park. But what is the motivation behind my project? The motivation behind my research comes from the very well-known statement to all of us that a structural system will transfer its loading only when the series of elements that compose it are successfully connected. This concept also applies in a wind turbine design, where several different parts need to be joined together to make the wind energy converter to operate as successfully as it does in the video. I hope that the video successfully plays. So introducing a new material to one of the integral elements of the wind turbine structure requires definitely a rigorous examination of the connection. And that led to the problem statement: how can a GFRP tower be connected with the steel support structure of offshore wind turbines? You can see with an arrow where is the location of my connection. And here you can see all the proposed connections. I'm not going to spend time into explaining all of them because I would use my other 7 minutes only into that. I will just describe the two that I investigated in more detail. So the first one is a bonded connection, is basically inserting the steel through the thickness of the GFRP and preventing it from moving by filling the gap with adhesive. A scarf geometry was given because it was concluded that it eliminates the stress concentrations at the top. And the second one is a bolted connection. It's a slip-resistant joint with preloaded bolts, and it is inspired by a standard bolted friction connection. But we made a very slight modification. We included steel sleeves around the holes inside the GFRP. The reason for that is going to come later. Starting with the bonded joint, the first question was that came to my mind is, which is the failure mode that is to be expected? I made a hypothesis that the steel to adhesive interface will fail first, and I had to somehow check that. So I switched to a much smaller and thus easier to test specimen. It's a double lap joint with steel adherents being the inner ones, and then GFRP as outer adherents. Performing these tests and then modeling the results would give me an answer to 3 questions. First of all, what kind of adhesive to use? Then, which is the failure mode to be expected? And third, what are the interface properties that I should input to my large-scale model? The easiest answer came answering which is the best adhesive was the easiest task for me, because the only thing that required me to do is to test 4 different adhesives. And the one that performed better was the one that was selected. Then to check the failure mode, I went to the force displacement graphs and I saw that the first crack happened in between the steel plates. And the second one indeed happened due to failure in the steel to adhesive interface. But still, I had no input about my interface properties. So what I did, you can see here, is that I went back to my experimental results from the IC. I drew 4 lines in the 4 interfaces, and I asked for the longitudinal displacements, meaning the ones in direction of loading. I did the same thing on my finite element analysis. I've subtracted those 2, and you can see at the top adhesive layer, I'm going to also point here the double up joint, yes. You can see that the top adhesive layer, the concentration of shear differential displacements are higher in the middle of the connection due to stiffness variation. And matching these lines from the IC with finite element analysis gave me an insight on the interface properties. Then I did an extra verification going back to my finite element analysis, where I asked from the software to show to me the higher shear strain concentrations, and it was proved that these were around the steel to adhesive interface instead of the FRP to adhesive interface. I had everything, so applying the current set of bonded parameters from the small scale joint to the larger scale resulted in a connection that can resist up to 90% of the external loading. I also checked if scale effects exist when upscaling a bonded joint, but unfortunately I cannot elaborate on that right now. Just keep in mind that the scale effects do exist. Then moving on to the bolted joint, similarly, I made a hypothesis that the connection will work only if the GFRP is not included in the preloading package. Otherwise, the GFRP material will be in direct contact with the preloaded bolts. I would have loss of preloading, introduction of stresses in the GFRP material that could possibly lead to delamination. But all this was an assumption that I made, and somehow I wanted to successfully capture all this with finite element analysis. So I had to input the correct properties for the GFRP material and for the delamination of it. So once again, I used experiments. I did coupon level experiments on material tests based on ISO standards. You can see here the tensile experiments that I did, the compression tests that I did, and the in-plane shear tests. And of course, I also did the 3-point bending experiment to quantify the interlaminar shear strength, which is the strength that leads to delamination of a laminate. I made also a finite element model for that to capture, to make sure that I use the correct input values. And then once again, I had everything from my final verification. All this info was used as input to my large scale model. And my hypothesis was proved. If the steel tube is not thick enough, compressive stresses are introduced to the GFRP material, leading to delamination that you can see here. And once again, it was proved that a smart use of steel, and by smart, I mean to use sufficiently thick steel sleeves, you can prevent the premature failure, and you can have a feasible connection that can withstand the external loading based on my finite element analysis. So my conclusions, these are the conclusions that I mentioned throughout the whole presentation. I'm going to highlight 2 of them that I put my focus on. At a steel to FRP bonded joint, the steel to adhesive interface will be the one that will fail first. And the second conclusion is that in order to have a feasible connection between steel and composite material, you will definitely need to include some sufficiently thick steel sleeves to make sure that you will prevent delamination. I want to thank you so much. I really hope that I inspired a couple of you in researching possible ways to connect the steel with other materials to create hybrid constructions that can elevate steel into a new dimension. Thank you so much.
Thank you very much, Angeliki. We have a couple of minutes for the jury's question or questions. Are there any questions from jury on this presentation. Yes, Andreas, please go on.
Yeah, I have a question. I don't think that fatigue was a part of these considerations, right?
You're completely true. It was not.
Also in the thesis, I didn't notice it. So how do you think you would proceed if you were to actually install a GFRP tower for offshore wind applications where fatigue is so dominant? What would be next?
First of all, I feel with these questions that I have to say, what am I doing right now? I am a PhD candidate. It's still in composites section at TU Delft. And I'm actually investigating the fatigue performance of a connection between FRP decks, it's not an offshore wind turbine in that case, with steel girders. It's definitely the next step, as you said. You start with static, you get your inspiration, you see if it works, and then the next step, the most logical one, is to dive into fatigue. It's the most important thing. I think also Christian mentioned a lot of it. The approach is to start quantifying stress concentration factors around the connections, regardless of which connection you use. I'm going to keep it a bit more general. And once you have this, you get an estimation of which are the magnitudes. I feel that it is inevitable that you have to go back to the lab and perform small-scale, downscaled experiments. And if you have also the possibility to apply these connections in a full scale and with some monitoring devices that you can take some data and you can actually compare and you can see how it will go from a smaller scale to a bigger scale, it would be the best approach.
Yeah, thank you. Thank you, Angeliki, for a very good answer. Do we have more questions? Just one more question maybe from the jury. In addition to fatigue issues, are there any specific questions on the presentation of Angeliki?
Yeah, it's Olivier. Did you look at cost issue? So compare to replace steel by this material?
So I was not the one actually that proposed this material. The research has been done. The thing that I did is somehow I had a feeling on when I had to select which connections that I'm gonna investigate further. So, for example, if a connection was to be manufactured in the lab and then you had to transport it together with the steel part, I would assess that it will be more costly. But the general idea, and I think the reason why they claim that the costs are reduced is because this GFRP material is very lightweight. So once you reduce the weight of the tower, you are able to reduce also the weight of the steel support structure that you have. In that case, it was a monopile foundation because it was the most common used in the North Sea. So the motivation behind them is that due to weight reduction, that will lead to cost reduction, and there is less maintenance when it comes to GFRP. It was a big part, so you didn't have to consolidate different parts and to connect them, so the maintenance would be reduced also in the future. And therefore, they had this idea that the costs will be decreased, but to be honest, it was not part of my research. I just read their claims to make sure that I know what it is about.
Okay. Thank you very much. We have to move on. Your answers are almost like half of your presentation long. So thank you for that. We have just to go on with the next presentation. It's Julia. I know just to say while Julia is preparing that it's 3-2 to companies because Angeliki is working at academia. So we go on with Julia. Are you with us, Julia?
Yes, I am, but I am not a host, so I cannot share the screen.
Oh, you cannot. Okay, just a second. We will see if we can do that. We can help you with that.
I hope you can.
Now you are co-host.
Yeah.
Frank has helped with that.
Yeah.
Please go on.
I hope you can all see my screen.
It's coming, yes.
Okay. Hello, everybody, and thank you for being here. My name is Julia Țăruș. I'm currently working in a design company in Bucharest, Romania, called Popce Asociații, and I'm going to present you my MSc thesis, which is evaluation of structural properties of high-performance steel performed on coupon specimens. My supervisors were both from TU Delft and also from Technical University of Civil Engineering Bucharest, my former schools, and also from ArcelorMittal Gandraj, who provided the coupon specimens. We're going to dive a little bit in a short introduction, then I'm going to present you the research methodology, the experimental procedure, and evaluation of results, and then we'll reach the conclusions. This research brings new knowledge about 3D printed material using wire and arc additive manufacturing, but this time using carbon steel electrodes. This is one of the first attempts to use carbon steel electrodes and not stainless steel. For the test, for the elastic part, we used a displacement rate of 0.015 millimeter per second, and in the yielding to fracture part, I used the 0.375 millimeter per second displacement rate at a photo frequency of 2 Hertz. Which means, of course, that I had to work with a huge amount of data. I personally analyzed around 35 gigabytes of data out of 120 gigabytes that were made for the whole project. I had around 100 pictures for every test, and I had to filter the picture, of course, so that the analysis won't last that long. We used the smallest type of specimen, which is in order to cut from the plate as many specimens as we could. And also the specimen were cut from the plate in a longitudinal, inclined and perpendicular direction from the printing direction. Also in the pictures you can see the roughness that is alongside or inclined or perpendicular to the cutting direction. I analyzed 8 mild specimens and 40 as printed specimens. The testing protocol was made in accordance to the American standard. The measuring technology was digital image correlation, and to validate and calibrate the results, I used finite method analysis with the objective of finding out material model for 3D printed materials using elastic plastic hardening and damage parameters. To first develop the stress-strain curves, I used the standard gauge length of 25 millimeters and 2 methods in digital image correlation, which are the facet point and the surface voice analysis. The gauge lengths that I used, that I monitored, were positioned on the edges of the specimen, like in this picture on the here and in the middle. Also, the 2 methods, the surface and the facet point analysis, gave me very similar results. Moving on to the stress-strain curves, I used the force that I obtained from the machine and the displacement that I extracted from the AC that I transferred into strains by the initial gauge length. And also I determined 8 TUD characteristic points that best describe the behavior of the material, which are the proportional limit, the yielding point, the start of the plastic behavior, then going to point D, which is the plastic behavior, the ultimate strength and strain, points E, F, G, and G that describe the post-necking behavior, and then the fracture strain. To determine the elastic material properties, for the modulus and Poisson ratio, I used the nominal stress range from 50 to 300 megapascals, using a classic method of determining both ratios. E modulus I deducted as a linear slope between stress and strain. For the yielding stress, I computed the 0.2% strain with the slope, the E modulus that I extracted from the test at the intersection between the stress-strain curve and the yielding point and the 0.2% strain. I found the yielding point. Finally, I put together all the diagrams for all types of specimens that I analyzed. based on either they were mild or as printed specimens, and also based on the cutting from the plate alongside, perpendicular, or inclined to the printing direction. As you can see, for all specimens up until the ultimate strength, the diagrams were almost identical, and after that they start to be a little bit different. Of course, I had to calibrate the material model. In the elastic stage, I introduced the E-modulus Poisson ratio and density in the model. Then for the plastic stage, I calculated the true stress and the true plastic strains. Moreover, in the coupled plastic damage stage, I calibrated to damage material, parameter W and parameter B, using the weighted average model. I calibrated the damage parameters for 6 mild coupons, which were the minimum and the maximum for the 3 cutting directions, perpendicular, longitudinal, and inclined, with the weight factor taking values between 0 and 1. After finding the suitable weighting factor for all the tests, I looked for the damage initiation point, searched for the corresponding stress for damage initiation, and from Abacus, I extracted the plastic equivalent strain. In the end, calibrating the damage parameters for all 6 coupons that I analyzed, the maximum and minimum of every cutting direction from the plate. Also, I made a comparison between the model and the digital image correlation. So in terms of plastic equivalent strain, the results are quite similar. For example, for this particular specimen in Abacus, I had this 61% plastic equivalent strain. And in DIC, I had the 60% plastic equivalent strain. So this demonstrates that the calibration was done correctly. Also, for these types of specimens, the roughness is really important. Even though in the beginning we measured all the specimens with a caliper, my professor scanned with a 3D scanner all the specimens, the raw specimens. He made 10 measurements for all the raw specimens with different position for the scanner, like in the picture above. And also 5 of the measurements were made on one side of the specimen and 5 on the other side. And then I analyzed all the data that he gathered. First of all, I compared the roughness profile for every measurement, extracted all the waves, put them together and shifted them to 0 to get the 6-degree polynomial that best describes one measurement for a raw specimen. Moving on, I put together all the measurements and obtained the final 6-degree polynomial, like in this picture here. That best describes the roughness of one specimen, and did that for all the 18 specimens, the raw specimens. I didn't use this in my thesis, but the roughness can be modeled in a 3D drawing program, like here, and introduced to Abacus. This is what I did with my professors in a journal paper to perfectly modulate the roughness surface of the specimen. It is also really interesting to see that for a thickness of 3 millimeters for the specimens, the roughness was really small, only around 0.2 millimeters. So to conclude, this material has an excellent behavior. It complies excellently with the provisions by Eurocode 3. Also, it seems that the mild and as printed specimens have very close behavior one to another, the longitudinal direction being a little bit more strong. And I think that this material can make an excellent impact in the future if used right. Thank you for your attention, and I'm waiting your questions.
Sorry, I was speaking without unmuting. I said thank you, Julia, for your presentation. We have a couple of minutes time for questions of jury. Are there any questions ready for Julia?
Milan, may I have it?
Please, Raffaele.
Okay, Julia, congratulations for this very excellent and comprehensive study on this test. I have just a curiosity because this is a high strength steel, and my curiosity is if you have also think to study the influence of the strain rate on the material properties.
Thank you for your question. To be honest, I'm not really sure. Right now, I'm not in school anymore. But maybe, who knows, in the future, yes, this might be really interesting to study.
Thank you.
Yes, do we have any more questions? If not, maybe
yes, just
the
very short one. First, congrats to this perfectly done work. Yeah, as you know, we have a challenge running here between industry and university. Can you tell us what you're doing?
I am working for 2.5 years, so solid working.
So it's a 4-2 for industry.
Yeah.
Okay, thank you.
Maybe it should be mentioned that
Please,
we at
Andrea.
universities actually also work sometimes, because it's sometimes people keep saying that they work. We also work, just so that you know that. Occasionally.
Yes. Thank you very much for that. We have now to open voting. Jury members have received their own link to the voting site, and this is a link for the public. Of course, we respect very much opinion of public, but opinion of jury is what counts, and we will announce in a couple of minutes results of the jury votes. So please take your time. You have only to vote once for your own favorite candidate. Vote for the public and for the jury. And we will be back in a couple of minutes to announce voting, just let's say 2-3 minutes maximum.
You run out of power? What do you need? Yeah.
Well, Frank, just to release the tension a bit, in the meanwhile, I want to say you look fantastic lying there in a bed of roses, even if they are not roses.
You're on mute, Frank.
It is because it's the Dutch Open Steel Award. We are inside the tulips and the windmills. And I also live very close to the Keukenhof, so maybe some of you have ever visited the Netherlands. Many people comes across the Keukenhof, which is at the moment opened, and so you can buy a slot there and enjoy the windmill and the bulb flowers. But yeah, it's
we have Christian who is 40, 36, Ben 27, Annelieke 9%.
Next to me is the head of the jury, and he is counting.
Yeah.
And it's too close to call, we say then.
But
yes, but Milan is spoiling by saying the results loud. Yes, to
no. It's a clear. We have a couple of more votes. It was 11 jury members who voted. I did not vote it yet, so I will not vote at all because I was involved in. I know some of this presentation in advance. 36% was voting for Christian, 27% for Ben. So we have a clear the first and second winner from the jury votes. And I will say what is the voting from the public. Public has voted similarly, actually 36% votes for Christian. 243 voters have voted. So 36% for Christian. And let me see down if I can.
Here, 35 for, this is the public voting.
Yes, and the 38 here, you have 38 and 35. So Annelieke and Christian are best candidates from public, but Christian is definitely the candidate number one, the winner number one from jury and from public, so absolute winner. And we have to apologize him for technical problems that we have. We will compensate that with a special video that we will make with him and put inside our recorded session for YouTube edition. It will be fine-tuned. So congratulations, Christian, for your first prize, both of the jury and the public, and congratulations to Ben for the second prize of jury. That is what we have today.
Yeah, maybe Christian wants to say something.
Yes. Well, first. The technique is not really working well for me today because my own laptop also crashed. I'm working from my girlfriend's laptop now anyway. Thank the audience for voting for me. I'm super excited. I cannot really explain this great feeling. I'm really happy. I didn't expect to be so successful with this thesis, and it's awesome. Thanks for this award. I hope many good editions will come. And I'm just very grateful. Also, thanks to my supervisors for always being very supportive and helping me achieve this great result.
Yeah, when it comes to the winners, we have one company and university. That's just for Peter's records, for Peter's note. So I think the most important for us is, of course, to produce students which find a way to the companies. And that is what is the case. I also have to say that 243 people voted for the jury, for the public. So you have received a very decent number of votes, Christian. So congratulations one more time.
Amazing. Thank you very much. Yes.
Can we hear some voice from Ben?
Ben.
Yeah, sure. Thank you very, very much for this it's a great honor that my master thesis has been awarded with second place. I think VAM is definitely one of the very exciting new technologies in steel construction and the whole steel industry. And I hope that I have made and will be able to make a small contribution to this through my research to help get it to a more broad adoption in the industry. So thank you very much again.
Thank you very much.
Yes, and thank you all for participating in this event. I would like also to thank again all. I have myself.
Oh, yes. Yourself. Here,
now
in the
now
flowers.
yes. Now we are in the flowers boat. So it was a pleasure having received so many excellent master theses. I have to quote impression from Leroy. Maybe Leroy, if you are with us, you can repeat what you said when we had the jury's session for evaluating the results. Leroy, are you with us, Leroy?
I am with you, Milan, and I can't remember what I said, but the quality of the submissions, the 22 written submissions, were all outstanding, and it was very hard to shortlist the 6. Yes. And then again today, the presentations were really excellent. And for me, this sort of shows the value of doing a master's, whether you go on to work in industry or academia. It's a really useful thing. And I think this award is great.
Yeah, thank you. To remind you what you said that the first 5 theses that you have checked were selected already. And then you said, I have to change my criteria.
You're right. I had to get stricter and stricter because, the quality was so good.
Yes, thank you very much. And thank you all partners from industry. I know that it's very difficult to find time for this type of activity. Of course, from academia, we see that as our duty. But from companies, I really appreciate your time. And I'm looking forward for continuing this competition. I don't want to call it competition. That's what I'm thinking how to call it. This is actually compilation of the best theses that we could find. And I don't know if Peter, Alan, or Jan would say something as industrial partners in that, because academics have a talent to take over all this type of workshop. So I have to devote special time for Peter, Jan, and then Alan, if you want to say some final words.
Yes, I'd like very shortly. I think all the students or ex-students deserve that they know what we said in the last jury meeting, in the first one. Yeah, everybody agreed that the work done is without any. All of them, are top of the top. Yeah. Then we had the meeting, so we decided for the top of the top of the top. Yeah, and what we did now is that we decided for the top of the top of the top of the top, I think, if I got it right now. I think everybody who worked on this so hardly deserves to know what we already said last time.
Thank you, Peter.
All the best for the future.
And can I agree with Peter's comments? And can I also say, first of all, congratulations, everybody. This has been my first experience of being part of such a process and seeing so many entries. And I, running the largest business in the UK, have been amazed at the quality and the variety of research going on in academia. And we, as a business, will be spending more time with, I hope, many of our academic partners in this process to find out more and see what more we can do in industry. So I think this has been extraordinarily helpful in trying to develop better links between the fantastic academic research that's going on and in industry. So I appreciate the invitation to be part of the process, and wish you all well, and thank you for your entries.
Thank you, Alan. Thank you. Final words is as follows. we are trying now to improve our submission. So we will organize submission which will be open all the year round. And we will organize a special templates so there is no so big difference between English written theses and the theses written in other languages. So we will have a little bit more fair presentation of the theses in certain template, but more of that information will be on Baumannsthal webpage and on ECCS webpage. So I think we will keep you posted about this information.
Yeah, and I think we will make a publication about this this webinar, and so everybody will have a good approach to this. Very useful information.
Yes, and then definitely we were talking about submissions which were not represented today. We will make a proceedings similar as Leroy has organized with. In UK, so the proceedings will be prepared proceedings will be prepared of the submissions that are sent to us. So with those words, I think we can thank you everybody for the presentation and your time, and hopefully see you next year, maybe even in a larger group.
Thank you very much.
Thank you and goodbye.
Bye.
Bye.
Thank you all.